Okay, so today we talk about solar granulation and the super-granulation structure. Solar granulation and super-granulation. So when we look up the sun's disk, we see a typical grain-like fine structures of the visible disk of the sun. We know that when we look at the sun's disk, it is the photosphere that we are looking at. And these grain-like fine structures, these are the granulations. These are typical features of the photosphere. So what happens is that within the envelope of sun, like within the photosphere envelope, what happens is that the radiative energy gets transported from the inner side, this is the radiative energy that goes up to the photospheric level. It has to be supplemented by convecting transport of energy. So something like this. The convections of energy. So we will study this convective transport of energy at some later point of time. But for the present time, we can see the basic. We can study about the basic model. The basic model is like this: there are convective cells of gaseous masks. So there are cells like this. Okay. This has a gaseous mass inside and has a particular energy. What happens is that these cells rise up. The more energy it has, the more light it is, and it rises up to the upper cooler layers. Okay, and then as it rises up in the upper cooler layer, it releases those energies, it transfers this excess energy, and then becomes denser and then falls back. So these cells, they go up and they fall back. So this is the way a convective transport of energy happens. And this process is repeated incessantly. So these rising and falling convective cells, they appear in the photographs of the solar disk as bright granules of various sizes. Now this, when you see the solar disk, it looks like that. These are the bright granules all over the disk, and within these granules there are darker regions. They are bordered by darker regions, and these granules are of various sizes. So we see these things when we look at the solar disk. Now this was known for a very long time. So we then send up balloons to, basically we have our atmospheric arrangement is such that we have a very bad seeing of the solar disk due to the turbulence in the Earth's atmosphere. So what we did is we sent balloons and got a better photographs of the solar disk. Then we sent balloons to about 80,000 feet in the stratosphere region, right? And there we got a much better view of the solar disk, and these granular stuffs are confirmed. And nowadays we have much better astronomical observatories that look at the sun, and we can capture much better photographs of such granules. So now these diameters of these granules, they vary from about 300 kilometer to about 18,000 kilometer, and a mean value is about 700 kilometer. Now what about their shapes? Their shapes are not really spherical. Their shape is more like polygonal, irregular polygon. So like this and this, with the intermediate space between the polygons. The polygons is completely irregular, and intermediate space are darker, and these are brighter. So these narrow dark regions is called the filamentary regions. Now the scientist K. Schwarzschild he suggested that the cellular structure, these arise from a non-stationary convection. Non-stationary. Non-stationary convection, and that is below the solar surface. So what about these filamentary regions? The filamentary regions are the inflow of the cool materials from the surrounding photospheric regions. So these are the convection cells. This goes up, and here this material is already cold, so these flow in between. So that causes these filamentary regions. Now the total number of granules on the visible disk of the sun is about 10 to the power 6, of the order of 10 to the power 6, which is exactly 3.5 into 10 to the power 6. So this many cells roughly is estimated. Okay, they can be observed as close to the limb, the solar limb, as about 10 inches, but are not observed still closer. So I mean, basically when we look at the solar limbs, we look tangentially throughout some higher layers, and in those higher layers the granules do not exist. So that's why we do not see those granules beyond 10 inches. Now the Schwarzschild has worked quite a bit on this area and have established various features of these granules. So for example, the lifetimes of the granules. Lifetimes of the granules. The lifetimes of the granules lets us know that how the convection of energy, how the convective transfer of energy actually happens. Now these lifetimes of these granules, these in the different regions of the solar disk are different. Okay. So there are photospheric granules. The photospheric granules, the photosphere being the white region, the photospheric granules have average lifetime of about 8 minutes. Photospheric granules, average lifetime is 8 minutes. Then there are the sunspots. The sunspots has two specific type of region. One is the umbra and another is the penumbra. Now the granules in the umbral region, okay, these has lifetimes about 15 to 30 minutes. And in the penumbral region are more, which is nearly about an hour. Okay. But the longest lifetime of the granules that occur in the facular region. What is this facular region? We will come to know shortly. Facular region granules has the highest average lifetime of 2 hours. This means that in the photospheric region, the convective transfer happens much faster than that at the facular region. Lifetime 2 hours means the cell that I see on the facular region stays for 2 hours. So that means the convective radiation transfer happens at a much slower rate. So these are the lifetimes of the granules. Then there are velocity patterns. So these cells, so these are the lifetimes and these are the velocity patterns. So these cells, they go up and come down. So what is the rate? What is the velocity with which it goes up? Now this velocity pattern we can study in two different ways. So now that we are talking about granulations, granulation essentially means that this cells has a velocity which is vertical velocity. And vertical velocity is easy to measure. How do we measure the vertical velocity? We measure through the Doppler shift. Doppler shifts of the lines that formed by the gases just above the granules. So this is the granule and it pushes the gas up. So the light originated from these areas. So this continuously pushes the light. So the light, this goes up along with the cell. Okay. So we measure the Doppler shift and the blue shifts of the lines formed by the gases in the granules. They indicate that these are the rising cells of hot gases moving upwards with a speed between 1 to 3 kilometers per second. With this speed, the cells go up. So these measured rate shifts of lines formed by the gases in the dark lines also indicate the downward velocity of the similar magnitude. So when we study the Doppler shift from these darker regions, or the blue shift, the blue shift gives us the upward speed, and the red shift gives us the downward speed, which is basically very much similar. Then once you do the detailed study of the velocity pattern in the photospheric gases, this has revealed that there is a larger structure of the granulation. A larger scale pattern. So a larger scale pattern. Pattern of granulation. This is what we call as the super-granulation. So this coarse super-granulation pattern, this is very similar to the pattern of this fine photospheric granulation, but these two are not same. These two are independent phenomena. Okay, not same phenomena. In fact, the average linear size of the supergranulation is about 20 times that of the granulation. So it is about 14,000 kilometers are the kind of average diameter of this large scale pattern, the supergranulation pattern. It is much larger, about 14,000 kilometers to about 30,000 kilometers. Okay. Now within this structure, the gas flows centered to edge. So these are the supergranulation cells. Here the gas flows centered to edge. So this way. So this is basically a horizontal movement. You see, so this is a vertical movement of the hot gas, and this is the horizontal movement of the hot gas. Okay, these photospheric gases thus possess two well-defined flow patterns. Vertical current of the fine granules and the horizontal current of the larger scale pattern, supergranules. With these two patterns of motion, they get superimposed, okay, to create the overall pattern. But there is also a third kind of pattern. Which is also independent. And this third kind of pattern is oscillatory. Meaning moving up and down all the time, and performs a complete cycle, like period of this oscillation is about 5 minutes. Okay, so now one can study the nature of this convection. Okay, which gives rise to this granulation thing. How do we study this? We will use the Reynolds or Rayleigh numbers. No, Rayleigh number. Now with these Rayleigh numbers that we know that if the Rayleigh number is high, that essentially means that the reason of the convection is a kind of turbulence. Okay, now how do we calculate this Rayleigh number? We calculate the Rayleigh number like this. So this R is essentially G into alpha multiplied by beta and L to the power 4 divided by K and Vk. And G is, as you all know, this is the acceleration due to solar gravity. So acceleration due to solar gravity. What is alpha? Alpha is the coefficient of volume expansion of a material. Coefficient of volume expansion. Then what is beta? Beta is the temperature gradient. Now you see that this beta we are using the absolute value because the temperature gradient can be negative or positive. Temperature gradient of the particular level that we are considering. L is the linear scale of granules. And K is the coefficient of the thermoelectric conductivity of the gas. And Vk is the kinematic coefficient of viscosity. This is how we calculate the Rayleigh numbers. And we say that when R exceeds some critical value R0, the convection starts. Okay. Now R can be increased by slowly increasing this beta. So we slowly increase the temperature gradient and then R can be increased. Okay, so what are the values of these things? So we already know that L is about 3 into 10 to the power 7. Alpha is around 10 to the power minus 4. This is for perfect gas. beta is about 10 to the power minus 4 for the layer that we are considering. G is 2.7 into 10 to the power 4. Vk is about 10 to the power 3. Is the atomic viscosity, 10 to the power 3. And K is about 10 to the power 12. This K we determined from the radiation field. Now when we substitute these values in R, we get R about 10 to the power 11. Which is very large. And why the Rayleigh number is so large? This indicates that the existence of a random convection generated by turbulent motions. Okay, so we see that this photospheric granulation, so this is for the photospheric granulation. This photospheric granulation is, we can say that it is a manifestation of a photospheric random convection motion. Okay, so it is the we term it as the sub-photospheric random convection motion. And this is originated by the very high opacity in the hydrogen convection zone within the solar envelope. Now that is these are the things that this granulation and the supergranulation are the very important thing in photosphere, and we have covered that, and then we will come to the chromosphere and then corona. But before coming to chromosphere, there is an important feature in chromosphere that we talked about, which is called the faculae. But these faculae also appear in the photosphere. So when we study the faculae, we will study in such a way that we cover the photospheric faculaes and the chromospheric faculaes together, and then we will come to the chromosphere.